The equivalent circuit model that we have developed to date has a voltage term that describes the open circuit voltage as it's a function of state of charge. We have an expression then that gives us state of charge. We also have a term that describes the instantaneous voltage drop when current is applied. And we have a dynamic term, this resistor capacity or RC term, that describes the non-instantaneous dynamic effect of applying or removing current. We've seen in this model so far a continuous time model of a cell or an ordinary differential equation. And we wish to convert this continuous time model into a discrete time ordinary difference equation, or an ODE, for easier use in our final applications, which are going to be discrete time applications. And I could do this, I could do the math, I could show it for the resistor capacitor model itself, very specialized to that. But there are at least 3 different variables for to which we would like to apply this math. And so instead of going down the very specific pathway of showing how to manipulate the resistor capacitor model to convert it to discrete time, I'm going to use a generic approach that we can apply in different situations, multiple different situations. So the generic model I would like to start with is an x dot equals a times x plus b times u. And the idea here is x is some dynamic variable that depends on its own value and on some input signal u of t, and a and b are both constants. We can derive from that equation the result that x of t, the solution to this ordinary differential equation, is that x of t is equal to e to the at times whatever initial value x had at time 0, plus the integral from time 0 to t of e to the at minus tau times b times u of tau d tau. So this first part is a response to initial condition, and the second part is a kind of a convolution. So if you've taken a linear systems or signal analysis course, this should not be any kind of surprise to see a convolution in the result of some system having a differential equation in it. But where did we get this result? Well, I'm going to go through probably the shortest derivation on the planet for this result. Maybe not, but it's the shortest I've seen for how do I get from here to there. And it's tricky. It's certainly tricky, but it's a very nice way of doing it, because it turns out that this method works for our case, and it also works for much more complicated matrix cases that we look at in other courses, like multivariable control systems. First thing I do is I take this equation and I rewrite it so that all of the x variables are on the left side, and then the b variable, the u variable, is on the right side. So I simply subtracted ax from both sides of the equation to get result number 1. To go from 1 to 2, I do something that isn't obvious, but it turns out to be valuable. And what I do is I multiply both sides of this equation in item 1 by e to the minus at. So I have b times u of t becomes b times u of t multiplied by e to the minus at. And I have x dot minus ax multiplied by e to the minus at. Let's look at this. I claim that that is equal to this. So in particular, let's look at this and see if my claim is true. And we have to remember the product rule in calculus to evaluate that. So this derivative in the center part of the equation, by the product rule, that's equal to derivative of e to the minus at by dt, all multiplied by x of t, plus e to the minus at times the derivative of x of t with respect to time. Okay, well, the derivative of x of t with respect to time is just what we've called x dot, so this is e to the minus at x dot of t. And we have to remember that taking the derivative of an exponential, derivative of e to the minus at with respect to time is negative a times that derivative with respect to time. So that there is minus a times e to the minus at times x of t. If we add those two terms together, sure enough, we get the left-hand side of equation 2. So we're going to proceed by keeping that and keeping that. And what we do to both of those terms is we integrate them from 0 to t. They're an equation. If I do something to one side of the equation and I do the same thing to the other side of the equation, they're the same, so I'm allowed to do that. So the left-hand side, notice that is copied, so this gets copied right there, and this gets copied right there. In the left-hand side, though, let's look at this a bit more. Notice that I've got d by d tau of something integrated with respect to tau, so the d taus cancel. So I'm integrating d something between 0 and t. When I integrate d something between limits, the result is that something evaluated between those limits. So it's something evaluated at t minus something evaluated at 0. And we know that e to the 0 is 1, so that's where the e to the 0 disappeared. We're almost there. To get the result that I would like right here, I have to move x0 from the left side of the equation to the right side of the equation. And then I need to multiply both sides of the equation by e to the positive at to cancel this. So e to the positive at cancels that, and then I've got e to the plus at there, and an e to the plus at there, which ultimately gets combined with the e to the minus a tau to give me this term. I'll let you go through that. This is, again, it's a very sneaky proof. Someone very clever came up with it. I don't know who. I don't even remember where I saw it first. But it's a very short proof that allows us to find the general time domain result for this ordinary differential equation. And it's expressed in a way that's very convenient for us, because what we're interested in is we're interested in now what happens if I apply a u of t over a time interval, and how does x of t change from one time interval to another. So I'm looking at discrete time instants of this equation. And I'm going to introduce some notation that I don't remember using before in this course. I use square brackets, so x square bracket k, to mean a point in discrete time, and I use the round brackets or parentheses to indicate a real point in time. So if I square brackets k means that time equals k times delta t, where delta t is the sample period. So I'm measuring at time 0. The next measurement is k equals 1 at t equals delta t. The next measurement k equals 2 at 2 delta t, and so forth. So we take this expression, and I'm interested in finding a difference equation, and thinking a difference equation is going to look something like x k plus 1 equals some variable or some equation times x of k plus some other expression times u of k. That's my ultimate objective, is to get something that looks like this to convert my differential equation into a difference equation. So I need to figure out what is that and what is that. So what is xk plus 1? Well, with round bracket notation, it's k plus 1 delta t. That's the time point I'm evaluating. And we know that that is e to the a times k plus 1 delta t. I just replaced t by k plus 1 delta t, notice that, times x of 0. And then plus, looking again, the only place t shows up is there, which I've replaced, and there, and there. So the integral from 0 to the new value of t, and e to the a new value of t minus tau, times b times u of tau d tau. We're going to focus our attention on this integral here, and we're going to break it into two different pieces. So note when I'm doing an integral of some function, I'm finding the area of that function between two points in time, and that's the same as the area under the function for that point in time plus the area under the function for that point in time. I can break up the overall integral into two parts as long as I'm integrating over the same total area, total space. I choose to break up that integral into an integral from 0 to k delta t plus an integral from k delta t to k plus 1 delta t. And everything else has stayed the same inside of the integral. So that is that, that is that. And I did do some factoring of this exponential. So I have e to the a k delta t and e to the a delta t factored out, multiplying x of 0 there. Oops. I'm leaving that alone. And now inside the first integral, I'm leaving the second integral alone too, but inside the first integral I'm then expanding this out. So e to the a times k plus 1 delta t minus tau, I'm pulling an e to the a delta t out. And then I'm leaving this e to the a k delta t minus tau in, which allows me, notice this is not a function of d tau, so that can come outside of this integral. And then I look at all of this stuff together and realize that's the same thing as e to the a delta t multiplying x of k. Think about it. If we went back to our expression here for x of t, plug in t equals k delta t, that's what I have down here left over inside of this integral and here. So all of this here, all of that gets collapsed to e to the a delta t times x of k delta t, or just x of k, which is where it goes in the next equation. The second integral I'm leaving alone temporarily, so there's no change there, there's no change there. So I'm getting close. I really am, because I want a difference equation. I want x, k plus 1 equals something times x of k plus something times u of k. And we just figured out what this is. This is e to the a delta t, is that value right there. Now I just have to figure out what multiplies u of k. Now to do this, we're going to make an assumption, otherwise it's not possible to solve this. We make an assumption that the input to the equation of interest is constant over this time interval k delta t to k plus 1 delta t. And so that's an approximation, because usually my input is changing in continuous time, but I'm just saying that for some period of time delta t, I can model it as relatively constant. That's probably too wide an interval to get a good estimate, so my choice of sample rate, my delta t, is going to depend a little bit on how quickly the input to the cell can change. If it changes slowly, then I can use a wide delta t. If it changes quickly, I have to use a narrow delta t. So with this assumption, we are going to look at that part of the equation. So the first part of the equation remains unchanged. But if u of t is constant inside from k delta t to k plus 1 delta t, it comes outside. And so I just have u of k outside of this. And then inside of this, there's a lot of things in this exponential that are not functions of tau, and one thing that is. So I break up that exponential into this part, which is not a function of tau, and this part, which is. Now I look at that integral and evaluate between those limits. So that stays the same, that stays the same, that stays the same. And integrating e to the minus a tau between limits is minus 1 over a e to the minus a tau between those limits. And I'm plugging those limits in. And so it's this thing evaluated at upper limit minus that thing at lower limit. Because of the minus sign, I evaluate lower limit minus upper limit. Same thing. And the dust settles, and I get this result here. xk plus 1 equals e to the a delta t times x of k plus 1 over a e to the a delta t minus 1 times b times u of k. I've now figured out what goes inside that second box. That goes inside of this box. There is a bit of a caveat. If a is 0, I have a divide by 0 in here, but I also have a 1 minus 1 in the numerator, and so I really get a 0 over 0, and that's a bit tricky. And you might be able to use L'Hopital's rule to figure it out. Didn't think about that until just this moment, but I can certainly go back to this integral here, and instead of having e to the a negative a tau there, I can integrate e to the 0, which is 1, so I can integrate a 1 instead and get the correct result down here. So it's a slightly different form for what you would get down below. So that's a very generic result. It's very abstract, but by the way, it works with the SOC equation. So z dot equals minus I over q. That equation, to get discrete time, notice that's another way of writing it is 0z plus minus 1 over q times I. So my a is 0, my b is minus 1 over q in that equation. And I have to be careful with this term here, the 1 over a term, but the 1 over q term is okay. So that, anyway, it all works out. So the SOC equation, I can use this general approach, but what I want to use it on right now is the RC circuit. And if we go back and look at the resistor capacitor circuit, what we have is that IR1, derivative of that with respect to time, is equal to minus 1 over R1C1 times IR1, and then plus 1 over R1C1 I applied of t. So in this equation, it's of the form we're looking at. My A is minus 1 over R1C1, and my B is plus 1 over R1C1. My X, the variable that I'm evaluating here, is the current through R1, and the input U is equal to the battery cell current I. So there are these correspondences between the equation that we saw in the last section and the equation we now know how to convert to discrete time. So xk plus 1 becomes resistor 1 current at k plus 1 equals e to the a delta t, okay, e to the a minus 1 over R1C1 times delta t, all times I R1, and then plus 1 over a, so that would be plus negative R1C1 would be 1 over a, times e to the a delta t, so I've done that, e to the a delta t is again e to the a e to the minus delta t over R1C1, and then minus 1. And then the b is 1 over R1C1, and all of those get plugged in right there. Small amount of cancellation happens. R1C1 gets canceled out, and this minus 1 reverses the order of this. So I can write it a little bit more simply as resistor current at time index k plus 1 equals some constant number based on the cell parameters times resistor current at previous time step plus some other constant number times the input current at that time step as well. So a lot of effort to get the general form of equation, but you see that once I have that general form, it's really very simple to put in the values for my resistor capacitor network to get a discrete time equation for it. So now I have a discrete time equation for SOC. Z k plus 1 equals z of k, and then it's minus eta of k over q times delta t times I of k. And I have this discrete time equation here for the resistor 1 current, and I still have the output expression for voltage, that V at time k is open circuit voltage minus IR1 times R1, and then minus I times R0. So I now have a full discrete time model. There's one other term that we're going to add to our model in the next section, but before we get there, I'd like to take a few minutes to talk about how do we find the parameter values in these equations. We've already stated that if I open up a cell, I don't find resistors and capacitors inside of it that I can yank out and put on an ohm meter or a capacitance meter to make my circuit model. These are just ways of describing the behavior using equations and elements that we're familiar with. So how do I find R0 and R1 and C1 in these equations? So this page is a way of getting approximate, what I'll call ballpark parameter values. We probably want to fine-tune the parameter values beyond what we get here using some later results in this chapter, but this is at least an initial set of parameter values that can get me pretty close to the final model. The thing that we're going to do in the lab is we're going to conduct a pulse test on the cell, where I have the cell resting, then I have a constant current discharge, and then I allow the cell to rest once more. And I need to know what the current is during the constant current discharge portion, and I need to be able to measure this voltage all the time through this test. I assume that I already know the open circuit voltage relationship for this cell. We talk about how to get that later on too, but here we're interested in R0, R1, and C1. If you think about the model we have, we've got voltage is equal to open circuit voltage minus IR1 times R1 minus I times R0. When I remove current from the cell at time 20 minutes in this test, the open circuit voltage no longer changes because state of charge is no longer changing. So any change in voltage is not due to this. So if I'm thinking about delta V, it's going to be due to the, let me write it out, is delta V is equal to delta minus IR1 times R1, and then plus delta minus I times R0. Now that capacitor voltage doesn't want to change instantly, so the only thing that's going to change instantly in the circuit is this I times R0, the moment that current is removed from the cell. And so we look at how much does voltage change the instant that current is removed, and we record that as delta V0, so the change in voltage at the instant, at the 0 point when I remove current. and that is going to be R0 times the change in current. I knew my discharge current. I know it's now 0, so I know delta I. And so now I can determine from that, calculate that from that, what R0 must be. So in particular, R0 equals delta V0 over delta I. And just to make sure it's positive, I'll put absolute values in case I missed a minus sign somewhere. Now the steady state voltage difference, when the cell is completely rested, we know in steady state the capacitor is completely discharged, so its voltage is 0. And the cell current I is 0, so the this is 0 and that is 0, so the steady state voltage must be only open circuit voltage. And therefore the overall change in voltage between time 20 and steady state is going to be the delta I times R0 plus R1. And we call the steady state change in voltage delta V infinity, and that's equal to R0 plus R1 times delta I. I know delta I. In the previous step here, I found R0, so I can solve this expression knowing this steady state voltage, which is this arrow. I can solve that for R1. And if my circuit has a single resistor capacitor network supplying the non-instantaneous voltage dynamics, its voltage of the RC pair will decay to 0 in roughly 4 to 5 time constants, and a time constant is R1 times C1. And so this period between the removal of current and getting approaching very closely the steady state is approximately 4 times R1 C1, and since I know R1 from step 2, I can calculate from that an approximation to C1. I checked, this is an actual lab test that's plotted here, and I looked at the results. And the current that had been used in the discharge was 5 amperes, and so 5 amperes had been removed at time 20 minutes. And the delta V0 is 41 millivolts, and the delta V infinity is 120 millivolts in this example. So I can compute from that. Okay, R0 is delta V0, 41, divided by delta I, 5, so that's a little over 8.2 milliohms. And R1 then, thinking about this, so R1 equals delta V infinity minus R0 delta I over delta I. R0 delta I we just said was 41 millivolts. So 120 minus 41 is about 80 millivolts divided by my 5. Apparently gives me my 15.8, almost 16 milliohms for R1. And if we look at the time to convergence, it's about 60 minutes minus 20 minutes, or 40 minutes. And 40 minutes in seconds is 2400 seconds. And so we might estimate that 4 times R1 C1 is about 2400 seconds, or C is about equal to 2400 over 4R1, which gives us a capacitance value of about 38 kilofarads. So just so it's not too opaque, not too mysterious, we can perform lab tests. From those lab tests we get voltage, current, input-output data, and there are techniques that we can use to convert that data into parameter values for our models. This is one example only, and it works for the simple model that we have seen. If our model was a little bit more complicated, such as if it had multiple resistor capacitor branches in series to try to better approximate the Warburg impedance, or if it has the hysteresis elements we look at in the next section, this approach does not work. We can use this approach maybe to initialize some values in the process that we will look at. The approach we'll look at later, this will not look, but at least it gives you some hope, some confidence, I think, that we can come up with a process to get parameter values for a model that we can then later on simulate and figure out how the cell will respond in different scenarios.